probably be making many mistakes because I forgot how this works. Also, I'm going to talk about some papers that I wrote mostly last year together with Alex Bellin and my student Diego Lisca and a few other collaborators, like that should be a K. Tarek and Julian Sonder and Franziel Nayak. But anyway, the subject is very close to what many people here in Stanford have been working on. So I will most likely insult several people in the audience because I forgot to cite them at the right moment with the right citation. So I apologize beforehand. And also, please interrupt any time that you want to discuss, because it's always nice to have some discussions, because over Zoom that was sometimes pretty difficult. So let's see if we still remember how actual seminars work. So maybe I'll just skip this given the audience, but anyway, so anti-de Sitter space is our favorite place to study quantum gravity. I'm briefly mentioning this because it's not always clear how everything that we say about quantum gravity, which we learned from our studies in anti-de Sitter space, actually apply in other spacetimes. Because the key feature of anti-de Sitter space, as I like to put it, is that it's a convenient box, so it's a convenient regulator of gravity, and it puts a boundary in space-time where quantum fluctuations die out, and it basically gives you a nice place where you can fix observables and other quantities. And this is precisely the sort of thing that is much more complicated in, for example, flat space-time. You don't have this nice boundary where things freeze out. You could try to impose boundary conditions by hand. But ADS is sort of the nicest box you can put quantum gravity in that really gives you some control and gives you a nice place to define obvious observables and so on. Now, the question I want to focus on very much in thanks. The question I want to focus on today is a little bit that we have this ADS-CFT correspondence is how much of the CFT, of that microscopic CFT, is captured by considering only semi-classical gravity in ADS, which is basically the theory in ADS that's accessible to semi-classical observables or low-energy observers. So I'm not going to talk much about treating some sort of semi-classical theory of gravity as an exactly solvable theory. I'm trying to take the point of view that semi-classical gravity is just an approximation to some complete theory. Moreover, it's a fundamental limitation, presumably for us as low-energy observers, that we can never see more than what's in semi-classical gravity anyway. And it's an interesting question then, how much we can actually uncover of the CFT of us or humans being only semi-classical observers. And you might have naively thought that semi-classical gravity corresponds somehow to, an ADS-CFT to a suitable version of a low-energy effective field theory for the CFT. But I think one of the fun things about ADS-CFT is that semi-classical gravity and ADS knows more than just a plain vanilla cutoff boundary theory. So now already the battery died. Sitting with one of his ears. Thanks. See, you forget all these all these technicalities of different presentations and so on. But it's interesting, I think, and a fun feature of ADS-CFT that the semi-classical theory also gives information that's more than what you would get naively if you would just take the boundary theory and put a UV cutoff in the boundary theory. And maybe this is part of this thing that's sometimes referred to as this UV-IR mixing that gravitational theories have intrinsically in them. For example, semi-classical gravity knows about the black hole entropy. You can compute it in a semi-classical gravitational theory. And for that, you can extract, for example, the approximate high temperature partition function of the dual theory for any value of the temperature, which is not something you would not normally be able to do if all you had was a theory of a cutoff, because you would not know what the density of states above the cutoff would be, and you would not know what the high temperature partition function would be. So there's more information than you get in the standard cutoff field theory. You can also use semi-classical gravitational methods to compute the partition function or many other things, many other Euclidean manifolds. finite temperature correlators. You can even get the page curve out, but I won't be talking too much about it because to get the page curve out, first of all, you probably know more about it than I do, but I also think it requires additional ingredients beyond just semi-classical gravity, because to even define the problem properly, you need to couple the system to an external heat bath, and you need to assume that you have infinite control over that heat bath. And I want to restrict mostly to just talking about semi-classical observers, so I'm not going to talk much about the page.
Yeah. Can you say what you mean by semi-classical gravity?
I'm being deliberately vague.
Okay.
We can talk about it more. And for now, I think just taking general relativity with perturbative corrections in Newton constant is fine for now.
Not wormholes and non-perturbative.
Well, wormholes, yes, because they're a solution of that theory. But for example, I'm not at this point not including brains in the theory that you can argue whether you think that's part of semi.
Wormholes are non-perturbative.
They're non-perturbative in Newton constant, but a solution of the classical field equations. So
that's what I want to know.
Yeah, no, wormholes will be included. Yeah. But I think there's a lot of possible answers to this question that might depend on exactly how you precisely define the word semi-classical.
But if you don't include brains, you're also missing some things. Low energy the system only know about, like baryons. So when you say you don't include brains, you mean only certain.
Well, if I don't include them now, you can decide to include them or not, and then the answers to some of these questions might be slightly different. Like you might want to include the baryon, which you could argue is low energy physics. Then those brains should probably be included in the new theory, but there's also brains that are much heavier objects, and those you probably don't. So yeah, okay. So there's a lot of definition issues there. Yeah, so to answer Lenny's point, of course, this is the famous factorization puzzle, which is that as long as you look at solutions of the field equations of semi-classical gravity, there seem to be correlations between copies of the same theory to the existence of wormhole solutions. And they led to this thing called the factorization puzzle, or whatever you want to call it. Because naively, this type of correlation that seems to be there if you believe this wormhole solution, this lack of factorization, there's many ways you can get it, but the simplest way is to introduce some disorder parameter in your field theory of some sort or another and do a disorder average, because if you disorder average theories, you correlate them. But the puzzle is pretty much that in standard ADS-CFT, for example, if you think about N=4 super-Yang-Mills theory, there didn't seem to be any necessity to disorder average over anything. Moreover, there's not so many things you can disorder average over. If you, for example, want your theory to maintain exact N=4 supersymmetry, then it's pretty much the only marginal coupling is the coupling constant, and the only thing you can do is put a little wave packet for the coupling constant. And that's pretty limited.
And
yeah, well, then there's a question whether averaging over n is something that is consistent with your low energy physics or not. You could say it's null because we can perturbatively try to compute the rank of the gauge group on the boundary. To leading order, that's n squared. At one loop, you find the -1 because it's SUN and not UN. And if you average over that one, you might find some disagreement with the fact that the theory is supposed to have a well-defined gauge group. So maybe averaging over n may also not be the thing that is compatible with semi-classical GR. It might depend on what question you're asking, but I'm not sure it's compatible with semi-classical corrected general relativity. Just thinking about the rank of the gauge group, for example. Now, this is the this wormhole. Now, if you look at the famous example, and that's the central hub of this example to some extent, if you look at two-dimensional JT gravity, then which is two-dimensional theory, then as everyone here knows very well, I'm sure you can show that this dual theory on the boundary is indeed an average theory. However, in this particular case, this is not the type of thinking I want to do, because this is derived assuming that the 2D theory is a fundamental theory, and you can solve it exactly. So you don't treat the 2D theory as some semi-classical theory, you treat it as an exact theory. And because of the special features of GAC theory, it turns out to be an exactly solvable theory. But normally in a semi-classical gravitational theory in higher dimensions, we are never able to do an exact UV computation, unless it's a BBS protected quantity or something like that. So the only thing we can have ever in a semi-classical theory is some version of coarse-grained information about the UV of the theory. We never are able to compute an individual energy eigenvalue from the high energy part of the theory. So semi-classical theories, almost by definition, give some version of coarse-grained information of the UV physics of the theory. That's going to be important. And the simplest example of such a coarse-grained quantity is if you, for example, think about the partition function of the theory, which you could compute by looking at the entropy of the black hole. Then if you look at the entropy of a black hole, even if you correct it with 1 over n, you find the smooth function of the temperature. And if you do an inverse Laplace transform of that smooth function in order to figure out what the density of states was, you will not find a sum of delta functions. Because typically, in order to get the sum of delta functions out, you would need to be able to do computations with an incredible accuracy, exponentially precise accuracy, and you simply cannot do any computation in a semi-classical theory at that accuracy. And that's why, even if you include loop corrections in your supergravity theory, you get some smooth function, and by an inverse Laplace transform, a smooth energy density of states. If we were able to do this computation more precisely, and we would find the sum of delta functions, that would be fantastic, because then we would be able to see all these individual microscopic degrees of freedom directly in the semi-classical theory. That would be a miracle, because A, it would seem to suggest you don't need string theory to solve quantum gravity. B, it would make loop quantum gravity people happy, I suppose, because that's precisely the starting point of loop quantum gravity. But to be in string theory, I don't think there's any evidence that this can be done in semi-classical theory, although fuzzball people might think otherwise. There are obviously exceptions, because if you look at things that are protected by supersymmetry and so on, then you can sometimes compute things exactly in the UV theory. But those are atypical examples. Now, the question is it conceivable that coarse graining somehow imitates disorder averaging? And this is the reason why one has these wormholes in semi-classical gravity. So it's kind of the key point that I want to make, is that, and this may have been said by many people in many different ways and with many different sentences, but I'll try to say it in my way, is that coarse graining is the thing that imitates disorder averaging, if you want. And that is the reason why we have wormholes. And to get some idea from this, you can think about the central limit theorem, which is simply a statement that if you take n variables that are taken from some probability distribution, and you take n copies of that probability, n elements of that probability distribution, you sum them and you take the average, and the average of this average is the average of the probability distribution. And the variance can also be computed and is equal to the original variance, but down by a factor of n. The central limit theorem is a much more precise statement, which says that the probability distribution of this sum converges to a Gaussian with some unit probability and blah, blah, blah. But this is an interesting thing to look at for a little bit. Because suppose we imagine that somehow all our high energy information is kind of chaotic and behaves for practical purposes almost like it was drawn from a random probability distribution. The toy example you can keep in mind is the decimals of pi. The decimals of pi is a very precise series of numbers. They're not even that complex because there's a very short computer program that produces all these numbers. So they're not as complex as we think the high energy spectrum of a strongly coupled gauge theory is. But nevertheless, if you have those decimals, They're for all practical purposes indistinguishable from a series of numbers drawn from a random probability distribution, where all the digits are uniformly distributed from 0 to 9. Now, if you believe that this is some version of coarse graining, so rather than computing the average, we compute an instance of this. So let me remove the brackets, the expectation values. Then I will get a number here, which is very close to x bar, but it will have erratic fluctuations around x bar, depending on exactly how we did our drawing. So the typical outcome of this coarse grain measurement is going to be something of the order of x bar, but it will have some erratic fluctuation. We don't know what this actual erratic fluctuation is, but we know its mean magnitude. Because the mean magnitude of this erratic fluctuation is given by the variance divided by n. And that is a robust statement. That does not depend on any erratic nothing. This is a robust statement. Similarly, if you remove the brackets here, this statement would hold. But again, there will be erratic fluctuations here that are given by higher order moments of the probability distribution, which you could also try to compute the magnitude of, but not their individual values. So the main punchline is going to be that the coarse graining that is happening in semi-classical theory is very much as in these equations, where the coarse graining of this thing here, so if you compute squares of things, then the coarse graining that the semi-classical theory is doing is not by coarse graining separately the individual sums and then multiply them, because that coarse graining which is given in this term is a slightly different type of coarse graining that you apply to this, which produces both terms. And both terms are well-defined objects. They don't have all the erratic fluctuations that are very theory dependent and so on. That are not the things I'm talking about. I'm talking about the robust features of this probability distribution. And this is a robust feature. And from a gravitational point of view, this would be represented by two disconnected solutions. Whereas this extra piece here is the thing that corresponds to the wormhole and this cartoon thing. So the statement is that the coarse graining that happens in the semi-classical theory of gravity is such that these wormholes compute a robust quantity, namely they compute the magnitude of the fluctuation around these individual computations. They don't give you the actual number, because that's microscopic UV physics, but they tell you something about the magnitude of the fluctuation. So this wormhole would therefore roughly compute for a sigma x divided by n, and these disconnected guys would simply be computing this square here. So this is roughly the picture. The coarse graining that happens in the semi-classical theory is precisely of this nature as shown here in the central limit here. So gravity can detect all the robust features of these probability distributions, and it can not detect the non-robust erratic features that are just given by details and so on. Yes?
Do you think for the purposes of this picture, we necessarily have to associate a meaning to the sum over I? Or is that unimportant? Like, we could average over couplings, or we have to choose what I means, right? In gravity, in the boundary theory.
Here, what I will mostly have, that this involves a sum over a band in the high energy spectrum typically. That's in almost all cases what I have in mind here. So there's no actual effort.
Ari, can I ask something? The slides have not been advancing in the Zoom display, or at least not in mine. The last slide I see is
Been on the same slide for a while.
still on the central limits slide.
Yes.
Yes.
All right.
Yeah, I'll soon move to the next one.
But can you say again what you're saying? I have the same question. What is this supposed to be up in the case here?
Yeah, so what one should have in mind here is, for example, any quantity that involves a certain amount of low energy observables typically involve a coarse graining of the high energy spectrum. So this would be a sum over energy eigenvalues in the high energy band of the theory.
But is that the usual EFT in the bulk? I think you're saying more than just that, or are you saying just that? Yeah.
The EFT in the bulk is doing some computation.
Yeah.
And but typically, if you, for example, look at these types of computations, this involves a sum of the high energies. So if you discretize this thing, it would involve a sum of the EI. And different EIs, for example, can be imagined as having some feature that is sort of random and a feature that is stable. So you should think of these sums over I, typically as sums over high energy bands of eigenvalues or something like that. It will typically, in my examples, the sum will end up being a sum of the high energy spectrum of the theory.
I think what it is, I understand is, what is the relation, and I think the answer is none, between this kind of coarse graining and the normalization? group?
Yeah, exactly. On the gravity side, there's a sense in which you integrate out the high frequency modes of the bulk field. But that is not to be confused.
No, it's not to be confused with this. This is not the RG of the, not at all the RG of the
Right, right. The
theory.
word sounded a little, so I'm just wondering.
Excuse me, can people hear? I think there's a comment that's probably worth making at this point. I think, and Jan can correct me if I'm wrong, that what he means is he's looking at a part of the high energy spectrum which is very, very dense. So the energy level differences are very small, but he's coarse graining over those very small energy level differences. In the low energy part of the spectrum, there isn't that much degeneracy, but the high energy part, the black hole part, has these incredibly tiny degeneracies, and that's the coarse graining. I believe that's what he means. So it's not like the renormalization group, which is.
Yeah, no, that's exactly right. Thanks, Tom. Yeah. Now, in some sense, the gravitational low energy theory just sees some indirect imprint of this. This is a CFT statement, not something we operationally do with the gravitational theory. And the imprint of this is on the gravitational theories in terms of the geometry and whether or not you have a wormhole. This is a picture, this is the proposal, and you need to find the evidence for this picture, obviously. But this is basically the idea.
As a low energy observer, are you allowed to compute any moment that you want? Or only up to?
Yeah, no, I don't think you can compute any moment. You probably can maybe compute up to order n in like a rank n gauge theory, but yeah, that's again a question of how much resolving power does a low energy observer have. Something like that, yeah. So it's not an arbitrary moment. Certainly not a correlation function that has e to the s operators in it. It's certainly impossible. So I would imagine if something with n squared operators in it is already basically impossible to compute accurately as a low energy observer.
We say low energy observer. What is that? If an observer can live for a very long time, it can be very low energy, but does have the possibility of measuring some very, very peculiar things such as quantum.
Yeah, great. So then we need to ask whether we can maybe come back to that a bit later, because it's a very interesting question whether we think that's part of the low energy theory or not. Yeah.
It is points it's sensitive to the high energy, to the details of the spectrum.
Yeah.
In a way which other things normally wouldn't be.
Yeah. So yeah.
But it's not really not obvious that it's a high energy.
If I can again make a comment here.
Sure.
If you're really averaging over bands in the high energy spectrum to do this, then you're precisely wiping out all of the quantum recurrence behavior. So it's really like what happens in hydrodynamics, where the hydrodynamic theory is a good approximation for long enough time scales, but also short enough time scales, because it can't see the recurrences.
Yeah. Thanks.
You're making this comment about order n squared things and also some things here. I mean, the example of the giant gravitons is a case where you really needed the UV theory, no wormholeology, just not too many states naively, but when you take into account the way the string theory works, with the brains and bars and all of that, you get the right cutoff on the state. So this is an order n squared thing. So maybe that's an example along the lines we we're just saying where.
Yeah, it's a bit like, for example, the 3D exclusion principle and so on. These are things because if you naively extrapolate the gravitational spectrum to high energies, then you would actually get too much entropy for the black hole and too little entropy.
Right, right. And the way that gets sorted out is through very much the UV physics.
That's right. And maybe to give a slightly different stupid example, just to get try to illustrate the idea. So suppose that we have a sum of phases that are randomly picked from the uniform distribution on the circle. And suppose you take the absolute square of this thing here, then this product has a robust feature, which is the diagonal, which is just equal to n in this particular case. And it has a non-robust feature, which is all these off-diagonal erratic oscillating things. And the idea would be that this robust diagonal feature is the thing that gravity is able to pick up, with all these erratic, fluctuating, annoying things, not. So in this case, the expectation value of this would obviously be 0 because these phases average out. But the average fluctuation, the average magnitude of the fluctuation of this is a robust quantity. It's given by the diagonal piece here. And that's the thing that the wormhole is computing. So from this point of view, semi-classical gravity is sensitive to the average size of fluctuations, but not to these individual fluctuations which would disappear under coarse graining, because coarse graining would wash away all those fluctuations, but it would not wash away the one here because it's a robust feature. Now you can ask in this particular example, because obviously this is an absolute square if these are actual phases, and you can ask what happens in the full UV theory, but clearly this thing should just be the absolute value squared or something. And there's several logical possibilities that might all happen depending on the theory that you look at. For example, it could happen that the actual wormhole here is unstable due to some UV physics mechanism. For example, there could be brain nucleation, or there could be other UV physics that destabilizes the wormhole. Then it's just gone, and then you could argue that this contribution is no longer there. It could be that UV physics simply adds those fluctuations back in. And then you have the full exact sum on the right-hand side, and then the thing factorizes. That would be a very simple, compelling way out. It's also possible that the UV theory is actually not dual to a single theory, but to an average of theories. And then there's no reason for, so if you put expectation values around the left and the right-hand side to make it an average, then obviously this equation is perfectly fine. And then you don't need to restore factorization in UV at all, and then it would just be an average theory. So those are logical possibilities about the UV completion of this particular low
You
energy.
say UV here, talking about some holographic, some field theory.
Yeah, yeah.
But then what do you mean by saying that's an average of theories? Is that?
It could be that the gravitational theory, that there exists something that you could call a UV completion of the gravitational theory,
Which is not itself just a.
which is not a
holographic
single theory. It could be an average of theories, but it could still agree with all the computations that you do in your semi-classical theory.
Okay, so you're just covering all the possibilities now.
This is just enumerating logical possibilities. Absolutely. Yeah.
There would be a different UV completion with the standard radius 15 or fixed.
Yeah, yeah. That would then be in. That would have to fall logically in class 1 or 2 and not in class 3, right? So somehow the picture is that this is just the cartoon of the spectrum of a CFT as you go from weak to strong coupling. So it's weak coupling with some nicely spaced energy spectrum. As you crank up the coupling constant, then the low energy sector of your strongly coupled theory gives rise to this famous large and integrable sector of the theory. But there's like above this value of the energy, it's roughly the threshold for black hole formation or phase transition happens. And above it is this very dense chaotic spectrum that is just not accessible to us at a detailed level. And so us, we are living here with these low energy observers. We are made from these integrable degrees of freedom in some sense. The only thing we can ever prove from this is sort of statistical average quantities.
When you say the low energy is integrable, surely ordinary low energy physics is not integrable.
No, but this is in the known supersymmetric Eigenstate examples, this is the structure that emerges.
So if I'm thinking about a low energy state with a handful of photons or gravitons, those gravitons scatter. Doesn't that make it non-integrable? When it scatter around,
I think if you translate that question in a large n correlation function in n equals super Engels theory, then that's supposed to be an integral correlator.
I don't understand why. If I have three particles, nobody can solve the three-body problem because it's not integrable.
The classical three-body problem.
I would say that the classical theory is not integrable. I don't think quantum theory is likely to be integrable. People keep saying this, and I don't understand what they mean when they say the low energy theory is integrable.
Well, the spectrum of this theory has been exactly computed.
Well, double traces all have anomalous dimensions.
The large n spectrum of n equals far super Engels theory is
The leading order
I
line.
can witness farmers saying there is no large.
yeah. This is the standard large n limit of the planar diagrams of the Gates theory. I'm not saying that all these correlation functions have been computed because that's very difficult. So the spectrum has been computed.
The leading order in N.
The leading order. The theory is not to lead. If you take a planar correlator and then it was super Engels theory, then it might be computable. It has not been done because computing correlates in integral theories is very difficult. But the spectrum of the theory, the leading term in the large n expansion, has been computed.
Certainly for finite n, no matter how big n is, it's not integrable.
Oh no, it's not. No. And it's also key that this is never in the integral region. So all the interesting physics is never in the integral region. So we
large n coupling is zero. Both coupling is zero, so it's not surprising that it's integrable.
well, it's not entirely trivial. I think that planar and super Engels is integral, but yes. Yeah, but it misses a lot of the interesting physics. In any case, it could even not be integrable as long as it has a sparse spectrum and it's part of the semi-classical theory. Then I don't. For me, it's not important. So in this picture, we have this low energy integrable sector, and then there's this high energy chaotic sector. And then the main claim that I'd like to make is that the semi-classical gravitational theory is the theory of the statistics of the chaotic sector. So all these many quantities that are sampled from this chaotic sector of the theory, you can think of these as pseudo-random variables. They're not really random variables, but for all practical purposes, behave very often like random variables that have erratic fluctuations that are not computable. And what the semi-classical theory is capable of doing is it's capable of computing the statistics of this chaotic sector. So if you take again the example of pi, you would be able to establish that the average digit is 4.5. And you would be able to see that the variance of the average digit is whatever 8.25 or something, or square root 8.25, I forget. And you could compute higher moments, and you could establish with a reasonable probability that those digits are sampled from a uniform distribution. But that is very different from writing down the actual digits of pi, which you will never be able to do. So it's in that spirit what semi-classical gravity is doing. And so it can compute higher moments of the relevant statistical distributions that you have in this chaotic sector. Up to a certain order, not infinite order, but some order that maybe is n, but certainly not higher. And it's insufficient moments to resolve individual values. Because if you have a probability distribution and it's only 3 outcomes and you can measure 20 moments, then you pretty much know what the numbers are, but that's not the situation here. The number of moments is much less than the number of values. And also, semi-classical gravity cannot distinguish what you call an average from a non-average theory, as long as whatever averaging is that you're doing, it yields the same moments of the statistical distribution. You just cannot distinguish the two. There's just no computation that you can do that tells you precisely, you know, the UV theory has a bit of averaging in it or not, because these two things are indistinguishable. And this raises a maybe interesting, maybe slightly philosophical question, whether there's like some fundamental limitation on how much information low energy observers can actually obtain about the high energy physics of the sea. Now, you can ask, is there any evidence for this picture? So, in the series of papers that was on the first slide, we basically try to explore this problem from the point of view of operator product statistics and to see if there's evidence for this picture. So, for example, look at the operator product expansion coefficients of some CFT. Those are well-known quantities that are extremely important in any CFT. And we're going to distinguish light and heavy operators depending on whether it's a low dimension operator whose energy is in this part of the spectrum, or it's a high energy operator whose dimension is in this part of the spectrum. I'll call those things L and H for light and heavy. So then the translation of this general statement to this particular situation would be is that semi-classical gravity has access to the statistics of these operator product coefficients, as long as there's at least one heavy index. There's the light OBE coefficient is just a low energy 3-point vertex, and you can just read it off from the Lagrangian. There's nothing to not much going on there. And so you can read off from your semi-classical theory the statistics of these quantities, but not their individual values. So let's see if you can actually do that. And that led to this particular slightly more precise statement, namely that all these things are really smooth functions of the relevant high energies multiplied by some matrices that are almost like random variables. They have a mean of 0 and a variance of 1. They can have higher moments. They will have higher moments. These are not exact Gaussian probability distributions. But the higher moments will be exponentially suppressed compared to sort of the variance, which is 1. So there should be some hierarchy of these, just like in the central limit theorem. All these higher moments are sort of suppressed by higher and higher powers of n. So simply we expect the higher moments of these OBE coefficients to be suppressed by e to the s or something.
So should you claim that these are universal for CFTs in a given dimension?
No, it may be
Not
better.
for CFTs, for semi-classical gravity.
Yeah, that's right. Yeah. So if you input some low energy physics, then there's universal results that come out. Yes. Yeah.
So that's where you can check that actually, like computing for a few different CFTs, doing the average, just check.
Yeah, if you have access to a nice large ends from the sure. Yeah.
Sorry, starting with the CFT, what is the probability distribution we're talking about again?
So we compute these OBE coefficients for some operators in the theory. And in this case, we take 2 low dimension operators and 1 high dimension operator that corresponds to an energy eigenstate.
And so far, it's totally deterministic thing about it.
This is in principle deterministic. But then if you would actually do that and you would make a table of these numbers, plot that, you plot the dimensions of these heavy operators and you plot these numbers.
So this is within a given theory.
In a given theory.
So you're saying is it or is it not? Does it or does it not fit with some probability distribution that you're trying to infer? Is that?
Yeah, that's right.
And
so these, if you make a table of these numbers, they would be weird and erratic. They might look like the decimals of pi or something like that. But you will be able to find that they have a particular average value. You might also be able to estimate the average variance of these numbers.
Given a list of numbers, you could do those computations. You can always compute those two things.
If you knew these numbers, we don't know these numbers in a strongly coupled CFT, we obviously don't know what these numbers are. We don't even have a precise list of the high energy spectrum of the theory.
Right, we don't. So how are you, and I said that again, I'm sorry.
So this is just a hypothesis, and then the question is whether you can find evidence for the hypothesis. This is the idea. And in some sense, ETH is a version of this statement. ETH is literally the statement, because ETH, so this is the Eigenstate thermalization hypothesis. It says that the matrix elements of a low energy operator between two high energy eigenstates has this diagonal piece in it. So let's ignore this one, that's important. And there's this piece here, which if you look at what this is literally a heavy, light, heavy OBE coefficient. That's exactly what it is. And the Eigenstate thermalization hypothesis says that in a chaotic theory, it's again an hypothesis, that this piece of this, this is basically this OBE coefficient, has a smoothly varying function of the energies in it times some approximate random matrix. So this is just the same statement as I was making, except I rephrased it in the language of operator product expansion coefficients, and also looked at other versions of it, but it's literally the same statement. So ETH is also the statement that as far as low energy computations in the condensed matter system go, you might as well assume that these numbers are random, because it's not going to change your low energy computation as compared to the actual numbers.
Sorry, quick question. In principle, isn't the OP coefficient the entire thing?
Yeah.
So what you mean to say in the previous slide is that the mean is 1 if I is equal to j, and 0 if I is different than j. Okay.
Very good. Yeah. So in general, there's this diagonal piece that I ignored, but it's obviously a principle.
Okay. Okay.
Yeah. Which one should take it?
Your sharp statement is you want to fix all of the C lights for light up to C over 24, some number. And then your conjecture or universal functions with some error.
The simplest version of this logic is the Cardy formula, where you input the Casimir energy, and then you do a modular transformation, and you get the entire high energy spectrum. Then you can add a few low-lying operators, and you can use these Tauberian methods and whatever, and you get corrections to the high energy behavior. It's very much like that.
You said they're not what these universal functions are yet, or?
Well, I can tell you what some results are that we know. So as I said, this Eigenstate thermalization hypothesis correctly reproduces thermal 1 and 2 point functions, and it has a nice other little feature, is namely that if you take a typical pure state, that it looks thermal. That's a very nice appealing feature of ETH. So ETH is a nice repackaging of some information, which is the typical states look thermal, and the thermal 1 and 2 point functions are in it. It does not make any new predictions besides that. So it's really a reinterpretation of some known facts in a kind of statistical language. So it's important that the input for ETH is all input which you have in semiclassical gravity as well. So that nicely sort of fits together. But none of this proves ETH. Because, and also, ETH does not require more input. So it's not like there's independent prediction in ETH. It's in some sense a reinterpretation of known low energy physics in terms of some statistics.
Sorry, can I ask one question? You were making an analogy to the Cardy formula. Is this literally the Cardy formula applied to genus 2 partition functions, because they're supposed to encode OB coefficients, or?
Yeah. That can all mention. But that's something that Henry and friends also did earlier. You can just use the genus 2, do an analog of modular transformations for the genus 2 partition function, and from that you get the statistics of C heavy squared, for example. I see. So how do you test all of this? So one thing that you can do is to try to use standard field theory techniques. And it's interesting to notice that these field theory techniques all originate in some sense in large diffeomorphisms in the gravitational theory. So they're really part of the low energy physics, they're just large diffeos. Because crossing symmetry is, for example, in a particular kinematic regime is this statement here. a 4-point function in one channel that's, for example, dominated by a light operator. In the dual channel will be given by a sum over lots and lots of heavy states in the dual channel. This is just crossing symmetry. But from this, you can sort of see how it works, but this is some known quantity here. But the right-hand side involves a square of C light heavy squared times some other kinematic stuff. And then you just need to make sure that this sum, whatever it is, reproduces the leading singularity on the left-hand side. And that will spit out the statistics for C light heavy squared on the right-hand side. In slightly more detail, if you put 4 operators on the disk and you do this light line diagram in it, so theta is the angular separation between these operators on the right and on the left. And on the left, the singularity is given by 1 over theta to the power 4 delta L from this short distance singularity and this short distance singularity. And on the right-hand side, in the dual channel, you get the sum over this H operator, C squared LLH. But now the kinematics does not involve this theta here. It involves cosine theta over 2, which is almost equal to 1 if theta is close to 0. So clearly, in order for this thing, which is very close to 1, to some power with some coefficients to give this singularity, these coefficients need to have a very specific form. And in some sense, what you can do here is that the right-hand side looks like a Laplace transform of C squared LLH. So in order to get the statistics of C squared LLH, you can start doing the inverse Laplace transform, and from that you get the statistics given here. So this is how you use low energy input to get a statistical statement of the averages of some of these coefficients. So this is an example of this way of thinking. And this is in principle a nice data computation that applies the principle in any dimension even. It's you can try to refine it in many ways, but this just illustrates the thinking. So this is an important thing you can do. You can apply it also to a more complicated 3-level diagram and get more complicated statistics. There's also some technology you can use in 2 dimensions, which uses basically all kinds of versions of modular transformations. I don't want to say too much about it, but there's all kinds of nice modular technology that you can use in 2 dimensions. Which again, I emphasize, modular transformations are large diffeos. It's kind of part of your semi-classical theory, this technology.
So even though it's kind of UVIR is all counts as part of the low energy source.
That's right, yeah.
Even though it's UVIR.
Because in some sense, you know, if you take the famous the solid torus of ADS3, you can interpret it in 2 ways. You know, you take the thermal circle to be the non-contractible one and the contractible one. It's all part of the semi-classical theory. It's the same saddle point, interpreted in different ways. So then you can just do all kinds of, I'm just going to list a few of these things that you can compute. So with this type of technology, by looking at all kinds of diagrams, including Hayes-Gide surfaces and so on, you can get all kinds of statistics of connected higher point correlators of these coefficients. And you can check that there is a nice exponential hierarchy in terms of the entropy S here. So as you go to higher and higher correlators of these OPE coefficients, as in the spirit of, say, the central limit theorem, you find a nice exponential hierarchy of correlators with rather strange coefficients in some cases. But this comes out, whatever comes out of the computation.
You have a silly question? Eigenstate thermalization probably doesn't require exactly the hypotheses that give you a weaker gravity rule in ADS-50. So presumably there are much stronger things that are true of gravitational theories that are true of Eigenstate thermalization.
Yeah.
Do you have an idea what kind of much stronger things there are?
Well, eigenstate thermalization does require the theory to be chaotic because otherwise these random matrices cannot be there. So I think for that chaos, so I think these random statements could apply in chaotic theories. If it's not a chaotic theory, they will not apply, but it does not have to be maximally chaotic. So it's quite possible that these statements apply also in theories that don't really have that weakly coupled gravitational duties because
they don't have that sparse spectrum energy.
Probably not so much, no. As long as you have as long as they're chaotic at high energies, I think that's the most important thing. But you could imagine a theory when you don't saturate the bound on chaos because of a somewhat denser low energy spectrum, and these things might still apply. Yeah.
There's some down on the other, that's just different.
I don't think we know precisely. So abstractly speaking, chaos.
ETH is a statement about a thermodynamic limit controlled by large volume, which is equivalent to very large operator dimension here. And I think the holographic theory, there's a different thermodynamic limit, which is like large central charge, large M. And then it means that it applies at sort of energies that are order the central charge, a large central charge, whereas it extends the regime, and that fits with these sort of modular variable flows. So it's
But with more specific assumptions on the spectrum too.
so yeah, like sparse spectrum means that it doesn't apply only at asymptotically high energies, but it applies at
It's also important that I mentioned that in like 2 slides or something, is that so there's some sort of averaging or coarse graining going on here. But I've not told you what the size of the window is over which you average. Because technically speaking, for example, this argument, this does not require chaos or anything. This is general CFD argument. So this result holds in any CFD. The difference between a free boson and a chaotic theory is that in the free boson case, you need to average over a big high energy window in order to get this thing going. Whereas in a chaotic theory, you only need to average over a narrower energy window. And the size of that window is presumably controlled by the low energy spectrum of the theory, because this is the sort of thing that you could try to study with these Tauberian technologies and so on. But the precise, I don't think there's a precise known theorem that gives a quantitative statement that if the spectrum at low energies is this and this and that the window over which you average has this and this.
So far in both slides, the examples have k bigger than 2, bigger or equal than 2, right? Yeah. So is there a way to actually constrain the 1-point function to show that it has 0 variance? Because in whatever bootstrap thing you do, there's always 2 or more of the coefficients.
So this 1-point function here is like it's just a torus 1-point function. So yeah, it's basically just diagonal piece of ETH. So that's just if this diagonal piece, so that we know already. I don't think there's a meaningful 1-point function here. Because you can always redefine an heavy operator by a phase. There's an ambiguity in how you define your operators or a sign. Like how do you pick your operator here? So I don't think there's there's a way to define the 1-point function here even in principle. Because you have no unambiguous basis to work with. No unambiguous operator basis.
Sorry, why is it wrong? Maybe this is naive. Why is it wrong to work with a primary basis in which the 2-point function of h is unit canonically normalized?
You could still flip the sign of the operator or multiply it by a phase if it's a complex operator, and that would affect the 3-point function. So you need to fix the phase of the operator unambiguously, and I don't think there's a way to do that.
Maybe we can look that up for it.
There's also absolutely no known computation that because you have external heavy lines, so
right.
Yeah, so there's also no low energy. Yeah. The main point here is that you get these things and that there's some technical computation so that you get a nice exponential hierarchy. That was the main point of all this computation. And you can even do more complicated things. So the general lesson of these annoying lengthy technical computations is that connected higher point functions are exponentially suppressed. We already discussed the window size, and you can also understand some of these qualitative behaviors using some other techniques that I won't discuss. So that seems to be the general lesson. So one way to think about the structure that you get is, since these OPE coefficients appear to almost be sampled from a random probability distribution, you almost could imagine that there is like something that looks like a Gaussian that computes all the moments of your probability distribution with some generating functional that computes all these correlators. That would almost make these heavy OBE coefficients into, you could almost think about Feynman diagrams, where this would be the generating functional for the relevant diagrams. And it's an interesting question whether we can find independent arguments for this thing to exist, to figure out exactly what index contractions appear and do not appear, And it's very interesting whether single-sided computations are sufficient to completely construct this quantity, or whether there is genuine new wormhole information that is not accessible by single-sided computations alone. And that's an interesting conceptual question, I think. I should point out that this random nature is not something that one proves. Presumably, well, we already discussed kind of that. And you can test the consistency of all these statements with some gravitational computations. But you can also try to now make predictions based on this. Because you can now predict new wormholes. If this whole story makes sense, you can also predict new wormholes. For example, this is not a new wormhole, but just for illustrative purposes, if you take the product of two genus 2 partition functions, there's 4 OPE coefficients here. And since we should think of these as being taken from this sort of generating functional with vertices and propagators, you can just draw some propagators, wig contractions. You can do it in 2 different ways here. There's like a disconnected one, which on the geometric side is the product of 2 disconnected geometries that just handle bodies that fill up the genus 2. And then there's this connected one that gives, and we check that these two actually give the same answer. This one agrees with the known Malmesine mass genus 2 wormhole. So even if you had not known about this wormhole, if you believe the statistical framework, you had computed the statistics just as propagator from the genus 2 partition function, which is one-sided information just using modular technology. Then you stick it into this computation, you would have correctly predicted the outcome from this genus 2 wormhole. Now, then you can also look at the genus 2. This is a slightly more obscure case, at the genus 2 partition function in a different point of moduli space. And you get this, but now there is also a relevant 4-point vertex from this diagrammatic point of view. This 4-point vertex here, you independently compute by computing the genus 3 partition function. So the genus 3 partition function at high temperatures gives you a connected CCCC 4-point function. Because you need to glue 4 3-pans diagrams together to make a genus 3 surface. And this is a 4-point vertex that in this example was not important. You can check it, it's subleading. But it's interesting that in this example, in this different corner of the moduli space, genus 2 surfaces, this one is actually dominant over this one here. And that suggests that if this whole story makes sense, there should be a new wormhole that connects genus 2 surfaces in this corner of moduli space that is larger than this Malmesine amount one. And you can compute its action based on all of this. So the prediction is there exists a wormhole, there's some weird genus 2 surfaces, and its partition function depends explicitly on the dimension of the light escape in the theory. So this follows from all these endless modular computations. And it would be very interesting to construct this wormhole, but it clearly must be one that is supported by matter, because otherwise the on-shell effective action would never depend on the dimension of the light escape of the theory. So it's a great challenge now to see if this wormhole can be constructed, because if this wormhole can now be found and one finds that Z is this, it will be very strong evidence for this picture that I'm presenting. And similarly, by just sticking to of the ETH type things together in a correlator, you predict the existence of a 2-sided wormhole before light operator insertion, which also seems to exist, although you need to complexify things, it's also a bit complicated. There's a large number of papers in this area, but it's an interesting prediction to work out and to also compute the actual numbers for this wormhole. So this is again a wormhole supported by matter, and to see whether it has the right magnitude as predicted by this simple ETH grid contraction. Okay, so this I am going to skip because of lack of time. And in the last few minutes, 3 or so, I just wanted to briefly mention that I think there's a very nice compelling picture here. That what you're computing in semiclassical gravity is high energy statistics. This is the right interpretation of what wormholes are computing, but the theory need not be averaged. But all these things together is self-consistent. But a broader question that you can ask is like, what we're trying to do is we're trying to parameterize our ignorance here. Because we try to write down some theory of the UV sector of the theory, but we don't know exactly what its sector is. We are ignorant about it. We have partial information about it. And statistical physics is precisely, in general, the theory that tries to describe a theory with limited information. And so you can ask, what is the type of generalization of statistical physics that we need in order to describe the ignorance of the full theory that the semiclassical observer has? The standard example in statistical physics is that you say, I know the energy of the system, E. And now I just write down the density matrix with maximal entropy that has that value of the energy. And if you do that, you get the thermal state out. So that thinking, I input some information that I know, and then I look for the thing that maximizes the uncertainty. That's a nice way to parameterize ignorance. That's what you do in statistical physics. In this particular case, you can ask exactly the same question. I have some low energy information, but I have ignorance about the full theory. What is the right statistical physics generalization that captures the type of ignorance that I have in this situation? And basically the proposal is that the type of generalization of statistical physics that we need is that we should replace the ordinary thermal state by a probability distribution on the space of density matrices. There's many reasons to believe that this is the right way to generalize standard statistical physics to the type of ignorance that one has in the semiclassical theory. And you can do a little exercise by repeating the standard steps of statistical physics. And for example, by simply saying, suppose I have a measure on the space of states, M of rho. And suppose I insert again the statement that somehow the energy has a particular value. Maybe you also want to keep the entropy fixed, but suppose you just want to keep the energy fixed, and you then want to maximize the uncertainty. Then you have to define what you mean by the uncertainty associated to a measure on the space of density matrices, like what replaces the entropy. It is a natural gas, which is a combination of classical and quantum entropy. Like basically you take the quantum entropy of each row and you weigh that with mu. And then this mu is like a classical probability distribution, which also has a classical Shannon entropy associated to it. You just combine the two things. And if you do that exercise, then you find that what generalizes Boltzmann is this particular measure on the space of density matrices. It is just a normalization factor times e to the minus s, the relative entropy of the state rho compared to the thermal state rho beta. This is originally, when we played with this was super fun because this is a very simple generalization of statistical mechanics. This has lots of features that are nice. For example, the fluctuations in rho are suppressed exponentially in the entropy, which is precisely what you see in ETH. You see that there are approximate unitary invariances emerging in microcanonical windows, which is also a feature of ETH. So this thing has many nice features that we see in ETH and so on. So it really seems to be in the right direction. However, if you work out it at a more detailed level, it turns out to have several annoying problems. So this is probably not quite the right answer yet, but I think it's a very interesting question. How should we generalize statistical physics to account for the type of ignorance that we see in low energy physics? Let's skip that and just conclude. So to wrap up, so semi-classical gravity, as I said, is the theory of the statistics of the high energy chaotic sector of the theory. It's consistent with wormholes and all that. And the picture is also consistent, for example, with this recent Schlenker written paper, which says that Wormholes only correct to the low energy observables non-perturbatively. So in this paper, they looked at partition functions on higher genus manifolds and showed that there is only sort of one topology that controls the low energy physics, and that all the other topologies at best give you non-perturbative corrections to the answer. That's consistent with this picture because it's related to the fact that these fluctuations and all the errors that you make are exponentially suppressed. So I think it's just self-consistent. I think this question of the right generalization of statistical physics is very interesting. It might also be relevant for many other systems like condensed matter physics, where I think one has to deal with the same problem. You don't know the detailed microscopic Hamiltonian necessarily. It's probably very complicated. You also have partial knowledge of the system. And you may want to try to parameterize that in a similar way. It's interesting whether one can apply bootstrap technology in this context as well. In some sense, bootstrap is precisely the same logic. In bootstrap, you input some low energy physics and you derive properties of the UV theory based on self-consistency and unitarity and analyticity. And many bootstrap computations give rise to sum rules. And the sum rules that one gets in bootstrap are precisely the same as these averages that I wrote down. You could say that, roughly speaking, where was it? You could almost say that this type of relation is like a sum rule, where you have a sum over high energy information and related to IR information. And the bootstrap produces many other examples of this. It would be nice to put it all together to see if the whole picture remains consistent. It's an interesting question whether there's genuine new information in wormholes or whether single-sided information is sufficient. I think it's an interesting question whether one can actually prove in these strongly coupled CFTs that the high energy sector is given by an approximate chaotic system, maybe random matrix theory. I don't really know how to even go about doing this. One way you could try to do this is by proving that somehow there is a sector of the theory that is reliably approximated well by JT gravity, even in high dimensional theories by some dimensional reduction argument or something. And you can use the known relation of JT gravity to random matrix theory. But I'm not sure if anyone has any idea how you could possibly prove this. I would love to know. You could look at the maybe at the spectral form factor, but that's a bit of a tricky thing to compute in high dimensions. And what would be sufficient? What would we think qualifies as a proof? Are there any other deep lessons for chaotic systems in nature? And more generally, it seems very difficult to really probe the UV at a detailed level that we would like to do. And maybe this is just something we should live with. Semi-classical gravity is just limited. We'll never be able to find all those black hole microstates in it. And finally, I think the message is semi-classical gravity from this point of view is averaging agnostic. It doesn't care. You can't tell. And the more details you add to it, depending on what you mean by it, you might be able to narrow the amount of averaging that you can do at most. But you will never be able to completely exclude the tiny bit of averaging from UV that you can detect with it. Sorry for going a bit over time. Thank you.
I have a question about the genus 2 guys. Before we start connecting two genus 2 guys to a wormhole, there is just a 3D handle body in which you fill in a genus 2 wormhole. Is that amplitude known from pure radius 3 gravity? And so that should have information about heavy square, right?
Yeah.
So what do we get from that? Just,
That's statistics.
Yeah, just heavy square.
Oh, yeah. I think it's just the k equals 2 version of this thing. What was it? I think this thing is still, yeah, for k equals 2, this is 10 minus 4 is minus 3 halves. That's right. So it's e minus 3 s over 2. Yeah. That's how it's going.
But you would predict some precise function multiplying this or something.
Oh, yeah, there's some precise. I suppressed all the interesting functions of other data because I was mostly highlighting the exponential behavior to see if this exponential hierarchy comes out. But for example, here you already see some more precise coefficients you can compute, and yeah, that's right.
Sorry, just a couple of questions. What Luca was asking about heavy, just the power one. So that's like a 3-hole sphere, right, with heavy insertions. And that seems like it should have a saddle point, right? Because if you have 3 insertions that are heavy on the sphere, you can put a negatively curved metric on it. So you just want to consider a boundary with a 3-hole sphere and conical deficits on that. So what is the ADS3 amplitude with that boundary?
It's 3 black holes in the book. You could ask this question for 3 conical defects, perhaps, which would be maybe interesting. But then you're below the black hole threshold. And this result is supposed to be above the black hole threshold. So it's like a 3 black hole amplitude. So that's very difficult to compute. Moreover, you would need to somehow, again, there's a basis ambiguity here. So I don't think it's a well-defined question.
But in a hierarchy, can't you just define the normalization of the operator such that, let's say, its thermal 1-point function is bigger than 0? It's positive. That uniquely specifies the sign ambiguity of the operator.
Yeah, maybe if you fix the convention in that way. Maybe there's a way to ask this question. Yeah. However, I would still, I don't know if there's like a universal magnitude that you can estimate. I don't know the answer. It's also a possibility that in this case, it's just very erratic and there's no average somehow that is meaningful. I don't know the answer. Now I need to think more about it. Yeah.
But those examples, you can't say perhaps like some boundary conditions that I can state in semi-classical language to define this state.
So for heavy, but what about the sphere boundary with 3 conical depths?
So that's light. If it's a light operator, if it's an operator that's creating a defect, then I think it's light. Yeah.
But, okay, it's light in some sense, but it's heavy in some sense. Then.
You know, you could also take 3 boundaries at finite temperature, and look at. So we know this 3 boundary wormhole in ADS3 that has 3 boundaries, which is computing something like this. And I think what you see, for example, is that if you take, so that is some sort of statistics of this heavy type. And roughly, if you remove one, if you ignore one, it really looks like black holes for all 3 of them. And I don't think it's very well known beyond the observation that if you ignore one of the 2, the other 2 look like BTZ. So maybe it's possible to get a bit more minus from these higher wormholes in ADS3.
Yeah, I just went into the on-shell action for that guy. So.
That example is literally the genus 2 guys.
Well, it's some half-cut open version of it.
Yeah.
I'm a little confused about the vision for low energy economy. Would you say that the states that comprise a black hole of, let's say, an energy and an entropy just at the Hawking page transition, would you say that's a high energy or low energy? Certainly low energy from the point of view of the field theory.
Sorry, why is this energies of order n squared, right? So,
Well, you can ask what the coefficients, like if it's 0.1 times n squared, and you're below the Hawking page transition, whether you still find that high energy or not.
Well, there's certainly nothing like the energies that the boundary theories have.
Yeah, I would think.
I would call those IR.
Most states still there are black holes, right? So the microeconomical is supported rather than the canonical, right? So there's still definitely black holes.
They're black holes, but they're low energy black holes. If I want a really high energy state, I pick a very high temperature black hole.
I think if you go through these, well, there is this fuzzy region precisely around this transition point. But naively, I would think that if you take anything whose energy scales with n squared, even if it's 0.01 times n squared, I would think as far as this discussion goes, it's part of the high energy spectrum of the theory.
But they're not part of a high energy spectrum of the quantum field theory. The quantum field theory has always high energy states out there around it. They're not that,
No,
definitely not that. Basically, what they are states above the Hawking page transition, that's all. But I think that's what it is.
anything above the Hawking phase transition is fine,
You call that high energy.
high energy. And if there is a slightly, like Henry was saying, slightly different ensemble, maybe microcanonical, that still makes it look like a black hole in the bulk, I think it's still part of the statistical description. If there's no way to have the state resemble a black hole under any kind of ensemble type of microcanonical, then presumably it's not. Yeah, that's probably the dividing distinction between them. For the sake of this type of statistical thinking.
So it's curious, as I said before, that the changing the physics of those of the ultra high energy physics states of the quantum field theory, those are the ones way out in the boundary. I don't think they would have much effect, for example, on quantum recurrences of a black hole, which was no bigger than the too high energy, too close now. So even though quantum recurrences of these incredibly delicate things, I don't think those UP states would be affected very much. On the other hand, any changes that you would make that would affect the spectrum that's in the black hole ensemble, those would drastically change. So I'm just trying to get what you mean by the high energy versus low energy. Quantum recurrences in that sense would be part of the high energy. Because they're dependent on the spectrum above the even though a low energy observer for sure could observe that if you live long enough.
Yeah, so that is well, I personally am not sure whether these types of timescales, for example, are longer.
Those are short time scales.
A very short compared to longer recurrences, indeed. But I'm not
I'm
sure.
going to an extreme limit, just like.
Yeah.
So really your observer recurs also, your observer is.
No, the observer is outside the system.
Oh, outside.
But he makes, but yes, but he doesn't have access to the very high energy states.
No, but it's comforting thought that we will have this talk again in e to the 10 to the 90 years or so. But yeah, so it's an interesting question whether these timescales are, and maybe this is not an unambiguous question, but whether we view these timescales as being part of the semiclassical theory or not.
Yeah.
Because typically, any e to the minus s correction in the theory could become important at this time scale.
That's right.
And in the semiclassical theory, we typically do 1 over n perturbation theory, but not e minus n. So you could argue that this is not really, strictly speaking, in semiclassical physics anymore.
I have one more question about the genus 2. Could you show the picture where the thing was detected? Yeah, this one. So I just wanted to understand the statement about the equation with delta chi.
Oh, sorry.
So now we have these 4 C's.
Yeah.
And you're saying that this third line here on this line comes from a genus 3 object?
Yeah.
And the genus 3 object, how does the delta chi come into the?
I didn't write it down, but it does depend on delta chi. So that's apparently also interesting. It's a high temperature. You're in a particular corner of the genus 3 moduli space. It's all high temperature, but if you do these modular transformations and so on, you pick up some dependence on delta chi, and the whole thing depends non-trivially on the light scalar in the theory.
So somehow the identity is not contributing to.
Yeah, that's right.
So it's like the contribution coming from the first non-trivial operator.
It's slightly reminiscent of these things where you compute a one-point function in the black hole background that you need like this extra loop around the horizon, and then therefore this light scalar controls this one-point function. So something like that happens there as well. So apparently, on the gravitational side, the leading saddle point for that genus 3 handle body should involve a matter field. Which is an interesting why or how. Maybe it secretly has a region where some phenomenon like this happens, although there's no external light operator. So I'm not sure.
Sorry, I didn't quite understand. The genus free thing is not a wormhole, right?
No,
It's
no,
just
no,
the genus free partition function, right?
You compute the genus 3 partition function.
Yeah.
From that, you get a 4-point connected correlate for the C's. And
Yes.
use that as input for this computation. Yeah.
Yes.
So that's like a 4-point vertex for this computation.
So all these wormhole solutions that exist in 3 dimensions, otherwise are just solutions to pure Einstein's equations. This would have to involve some stress tensor backreacting.
Yeah.
Presumably.
That's what seems to come out. Yeah.
Okay.
How do they connect to it? Because you have none of the indices on the left match with indices on the right, so it's not like they connect because they're.
No, that's right.
various
So there is some 4-point vertex, and the 4-point, it's a vertex, and that 4-point vertex will make some of these indices equal to some of these. That will be enforced on you by this 4-point vertex. So I forget the combinatorial structure here, but clearly all these indices will be connected. So they're by this 4-point vertex. Yeah. So the total sum of there are 6 independent indices here, but once you stick in this vertex, there's a sum over 4 indices left or so. Yeah.
Well, we've had a lot of excellent questions and discussion, which will hopefully carry on for the rest of the week. So with that, let's thank Jan again.
Yeah.